Okay, welcome everyone to lecture 8 of this course on nonlinear and adaptive control. In the last class we had studied how to design adaptive controllers for plants with external disturbances where the structure of these disturbances may not be known, or there could be unmodeled dynamical effects. We had discussed that we could design a robust controller to account for such effects. But since the focus of this class is adaptive control, we are in fact going to robustify the adaptive update laws. So, in the last class we had discussed one of the ways in which we can add robust elements to these classical adaptive control laws. We had studied the dead zone approach, where within a dead zone there is no adaptation. The adaptation of the parameter estimate happens only if the error is greater than a certain threshold, and this threshold is dependent on the upper bound of the disturbance. So, if the error is larger, then the classical adaptive control laws will be used. Once the error becomes smaller than the threshold, which is called as the dead zone, there will be no adaptation. So, what this ensures is that the parameter estimates stay bounded for all time. So, using this approach we are able to guarantee boundedness of all the signals and also the control input. The one of the features of this technique is that the upper bound of the disturbance is required to be known. However, in many cases we do not know what the upper bound of this disturbance is going to be. So, this is a very practical situation, because we may not we may not be able to figure out what that upper bound d bar would be. So, in that case, is it possible to still guarantee that the parameter estimates always remain bounded? So, in this class we will talk about two of these techniques. So, the second technique for a robust adaptive control is sigma modification. So, it does not require the upper bound of the disturbance. So, although we know that the disturbance is upper bounded by d bar, but d bar is not known. So, we of course cannot use the dead zone in this case, because we will not be able to indicate what that dead zone is without knowing the value for d bar. So, what can be done in this case? So, we can use the following sigma modification adaptive laws. So, k x hat dot we had designed previously was given by minus gamma x b transpose p e x transpose. So, what we do here is we add an additional term which we call as the sigma modification term, like this. So, this is the adaptation term, rather let us not put it this way, we just say that this term is the sigma mod term or the leakage term or the damping term. So, we do the similar modification in the update law for kr hat. So, what do you think this term can do? So, if you look closely, this term consists of this sigma x and sigma r, which are positive constants, and it also includes k x hat. So, this is k x hat dot, and then we have a minus k x hat. So, this term has a damping effect on k x hat. This can also be thought of as a stabilizing effect on the k x hat dynamics. It is very similar to when we have x dot equals minus k x. So, in that scenario, x would decay and go to 0. So, similar effect is provided by these two terms, where the first term is the adaptation term, where the k x hat and k r hat are trying to learn the ideal values of k x and k r, and just for the purpose of stabilization we have these damping terms which try and slow down the adaptation of k x hat and k r hat and make sure that the estimates remain bounded for all time. So, of course, we need to prove how Lyapunov stability or boundedness can be proved in such a scenario. So, let us go ahead and jump into the Lyapunov analysis and see if these modifications can indeed lead to some notion of stability or boundedness. So, let us consider the same Lyapunov function candidate as before. So, V is given by E is a function of k E k x tilde and k r tilde is given by half E transpose P E plus half trace of k x tilde transpose gamma x inverse k x tilde plus half trace of k r tilde transpose gamma r inverse k r tilde. Okay, so this is our Lyapunov function candidate. So, now we go ahead and take the time derivative. So, we can skip a few steps here because it is a repetition of what we have done many times in this course so far. So, take the time derivative, and V dot is given by minus half E transpose Q E plus E transpose P D. This term is coming from the disturbance which is acting on the plant, and then we have a minus trace of k x tilde transpose gamma x inverse, and then we use the adaptive laws that we have mentioned here. So, say minus gamma x B transpose P E x transpose minus gamma x sigma x k x hat. Similarly, for k r hat, we substitute for the adaptive law. Okay. Further, we of course I missed the terms from the tracking error dynamics, which are cancelled by these adaptive laws. So, we have this minus x transpose kx tilde transpose b transpose p e minus r transpose kr tilde transpose b transpose p e. Okay. So we have seen before that these terms in fact get cancelled by these adaptive law, the classical adaptation terms in the adaptive law, and what we are left with is this damping term, and let's see how this damping term helps in accounting for the for this E transpose P D term, which is a disturbance term. Okay. So let's look at V dot now. So V dot is minus half V transpose Q E plus E transpose P D plus trace of Kx tilde transpose. Sigma is of course a scalar and can be moved out. Let's have it here right now, plus trace of kr tilde transpose sigma r kr hat. So now we can substitute for kx hat and kr hat here, and we know that kx hat is kx minus kx tilde and kr hat is kr minus kr tilde. So what we get is V dot minus sigma x trace of kx tilde transpose kx minus sigma r trace of kr tilde plus sigma x trace of kx tilde transpose kx plus sigma r trace kr tilde transpose kr. Okay. Now I am going to consider an aside, and I'll come back to this expression a little later, but as an aside I want to talk about the Frobenius norm and the Frobenius product of a matrix. So you may be aware that the Frobenius norm of a matrix is given as defined as the in fact the square of the Frobenius norm is defined as the sum over all the elements of the matrix of the square. So it's basically the square root of the sum of the squares of the elements. So aij square which is also same as the trace of A transpose A. Okay. So, in general, the Frobenius inner product of matrices A and B is denoted by this expression and is given by the element wise product of the elements of A and B. So, what we have is overall elements Aij times Bij, right, and this is also the trace of A transpose B. Further, using the Cauchy-Schwarz inequality, for inner products, we can say that the norm of this inner product is less than equal to the product of the Frobenius norms of the matrices A and B. So, this is same as writing the trace of A transpose B is less than equal to the Frobenius norm of A times the Frobenius norm of B. This is using the Cauchy-Schwarz inequality. Okay, so now using this aside, we can now go back to the Lyapunov derivative. So, here what we can see, oh, so there is a slight error here. So, we have a, okay, now it works. Okay, so what we can see here is that the trace of kx tilde transpose kx tilde is same as saying that this is the square of the Frobenius norm of kx tilde. Similarly, this is the square of the Frobenius norm of kr tilde, and this can be replaced by, this can be in fact upper bounded, the norm of this can be upper bounded by the product of the Frobenius norm of kx tilde times the and the Frobenius norm of kx, similarly for this term. So, now we can upper bound this expression of V dot as, so the first term we can upper bound like we did before, and we can also take the upper bound of the second term, which is the disturbance term, by using the maximum eigenvalue of the matrix P times the upper bound of the disturbance d bar times the norm of V. So, although d bar is not known, it is okay for this to appear in the Lyapunov analysis, as long as it does not appear in our control or adaptive laws, it is fine. Okay. Then minus sigma x of kx square minus sigma r plus sigma x of plus norm of kr tilde times Frobenius norm of kr. Okay. So what do we see from this expression for v dot? So what we see is that this term is good because it's a negative term. This term is also good because it's a negative term. This term is good because it's a negative term, whereas all the other terms are not so good because so those are positive terms. So we need to find a way to dominate these positive terms using these negative terms. Okay, so one way that we can go ahead with this analysis is by combining these terms. So let's say v dot is less than equal to minus lambda min of q so I take it outside, and then I have E minus 2 lambda max d bar over lambda min of q Similarly, I combine the other terms, minus sigma x kx minus sigma r Now, what we can say from here is that if you look at these terms in these square brackets, and if these terms are positive terms, then we can say that v dot is less than equal to 0, and since v is positive and v dot is less than equal to 0, what we can say is that v is bounded, and we can further say that the error states E, kx tilde, kr tilde are also bounded. So we can construct a set. So let's construct a set given by this and such that norm of E is less than equal to 2 lambda max of p lambda min of q times d bar comma kx tilde f is less than equal to kx and notice here that the norm of kx is simply a number. So although we don't know what that number is, but it's a constant. So kr tilde is equal to kr f. Okay, so this is the set definition. It's basically all the values of E, kx tilde and kr tilde such that these errors are less than equal to some constant. That constant may not be known, but as long as they are within these values, we say that they are elements of this set. So, this is a compact set, right. It is a compact set where we say that the all the errors are in fact bounded, E, k x tilde and k r tilde are bounded, because the right hand side here are all these constant expressions. Okay. So, if your states are outside this set, so outside this set we say that if you are outside this set, then these terms in the square bracket are in fact positive, right, and which means that V dot is in fact less than 0. So, it's negative definite, because this includes all the 3 states. So, norm of E, norm of k x tilde and norm of k r tilde. So, none of the states is missing here, and that is why we say that V dot is in fact negative definite, not negative semi definite. So, if you are outside this set, then V dot is less than 0, which means that V will monotonically decrease. Okay. So, V monotonically decreases from its initial value V of 0, and in finite time it till it enters so V monotonically decreases till the states E, k x tilde and k r tilde in fact enter this set, and inside this set of course we say that the states the error states are bounded, and because outside of this set since V is positive, V dot is less than 0, then we can say that V is bounded and E, k x tilde and k r tilde are also bounded. So, again what we have shown here is that all the error states, the tracking error states and the parameter the estimation error states are bounded for all time. So, outside the set V dot is less than 0, which means that V monotonically decreases from its initial value, which means that the tracking error, the parameter estimation error would stay bounded. Inside the set we cannot say about the sign for V dot, we cannot say whether V dot is less than equal to 0 or greater than 0, since this is the size the sign of V dot is unknown, but what is known is that this is a compact set where all these states, the error states are bounded. So, in both the scenarios the parameter estimation errors are bounded, and hence we can say that this sigma modification leads to boundedness of the parameter estimation error. Alternatively, we can do this analysis in a more rigorous way. So, we can either prove by using the method that I have just shown, or we can proceed with the Lyapunov analysis starting from say this equation. So, let us call it equation star. So, let us proceed from star and see how alternatively we can prove that the parameter estimation errors are bounded. In fact, we can probably say more than that. So, starting from star, so we can use the Young's inequality, which says that norm of A times norm of B is less than equal to square plus norm of b square by 2. So, we use that on certain terms in this expression. So, we use that on this term, and we use that on this term, and we use that on this term. So, on these three terms, in fact, we let's not use it on this term. So, okay. So, we can say that v dot is less than equal to. So, let's split the first term into two equal parts, and we will see why we are doing this. So, this kind of manipulation you should get used to doing when doing this Lyapunov analysis, because this is used to upper bound certain terms and also damp out certain positive terms. So, we are dividing this into two parts. Plus what we have is lambda max times d bar times E. Okay. Then what we have is the negative terms involving kx tilde square. We also have so then we use the Young's inequality, and what we get is sigma x over 2 kx tilde square plus sigma x over 2 kx square. Similarly, for kr tilde, we get sigma r over 2 times kr tilde plus sigma r over 2 kr square. Oh, so sometimes I forget the Frobenius norm. I hope that you understand that wherever I am missing it, I mean that these matrix norms are in fact Frobenius norms. So, now let us consider this this term here. Let us consider this term here and try and manipulate this. So, what this term is, it is minus lambda min over 4 p square plus lambda max d bar norm of E. So, let us complete the squares. Okay. So, completing the squares. So, how do we complete the squares on this expression? So, we add the so we have a minus a square term, for example, and this is say our 2ab, and what we need to get is a minus b square term. So, from these two expression we extract what b is, and then we add and subtract that term. Okay. So, let us for this case let us complete the squares, and what we get is our a in fact is square root of lambda min of q divided by 2 times E minus, so the b is lambda max divided by square root of lambda min of q times d bar square, and then because we add and subtract, the term that we subtracted is used to form this square term, and the term which we added is left as a residue. So that is lambda max square d bar square over lambda min of q. So you can work this out. So if we substitute for this in the expression above, what, so we just replace this whole expression instead of this. So then what we can do is we can ignore, or we can throw out this negative term, and what that will do is that will further upper bound v dot. So we can further upper bound v dot by throwing away this negative term. So what we are left with is v dot is less than equal to minus lambda min of q over 4 e square plus lambda max of p over lambda min of times d bar square. Okay. Okay, and then we have the other terms. So minus sigma x over 2 kx square minus sigma r over 2 kr square. Then we have these positive terms plus sigma x over 2 kx plus sigma r over 2 kr norm square. Okay. So now we collect the negative terms together and then the positive terms together. So what we get is v dot is less than equal to minus lambda. So we just rearrange here. Minus lambda x over 2 kx tilde square minus lambda r over 2 kr square, and then we have the positive terms. Okay. So what we see from here is that all these positive terms are in fact constants. So let's call them as C. Okay. And what about these negative terms? Can we somehow collect these negative terms and comment on how v of t evolves as t goes on? So what we have to do for that is first to go back to the Lyapunov function. So remember, the motivation here is that we want to collect all these terms and into something which is a function of v. So we will see how that really helps us. So but just as a detour, what we look at is the original v. So v, if you remember, was half E transpose P E plus half of trace of kx tilde transpose gamma x inverse kx tilde plus half trace of kr tilde transpose gamma r inverse and kr tilde. So can we upper and lower bound v in terms of norms of these errors? So we can in fact do that. So v can be upper bounded by lambda max of p times norm of e square plus, again using properties of trace and Frobenius norm, we can say that this is half of lambda max of gamma x inverse Frobenius norm of kx tilde square plus half lambda max of gamma r inverse norm of kr tilde square. The lower bound can similarly be calculated as lambda min of p e square plus half lambda min of gamma x inverse kx tilde square plus half lambda min of gamma r inverse kr tilde square. Okay. So now can we collect these error terms together? So again we can further upper and lower bound these expressions for v as, so v is, so remember this is a detour, we were on v dot and we just now started developing the upper and lower bound for the Lyapunov function itself. So if we consider the maximum coefficients of all these, then we can further upper bound v using the maximum of lambda max, so maybe 1 over 2 the maximum of lambda max of gamma x inverse and lambda max of gamma r inverse. So we can times what we have is norm of e square plus norm of kx tilde square plus norm of kr tilde square. Similarly here we can have half the minimum of lambda min of p lambda min of gamma x inverse lambda min of lambda r inverse times norm of e square plus kx tilde square plus kr tilde square. So it became a little untidy here, but I hope you get the idea. So what we can in fact say in a tidy way is that v can be upper and lower bounded by some lambda 1 times e square plus kx plus norm of kr. So let's make this as lambda 2 and lambda 1 of e square plus kx All right. So, now can we use that in our expression for V dot? So, we can again rewrite our V dot by collecting these negative terms together. So, if you look at V dot, we can collect these three terms together, and we can further upper bound V dot as, so coming back to V dot. So, the detour ends here. So, V dot is further upper bounded as minus minimum of lambda min of q lambda x over 2 lambda r over 2, and then we have, so this is how we collect these terms together, and we will see how this helps us. Plus c. Okay. So, now we can say that we can use this equation number double star, and we can replace this term in the square brackets by something which is smaller than that. So, which is v over lambda 2. So, we see here that v over lambda 2 is smaller than the sum of squares of these error terms. So, we can, if we replace v over lambda 2 in place of these square brackets, we end up further upper bounding v dot. So, what we do is we say that v dot, sorry, so using, let us use this, using v dot is less than equal to minus minimum of lambda min divided by lambda 2 times v plus c, right. Let us call this coefficient of v by alpha. So, then we can write v dot as minus alpha v plus c. Okay. So, what this means, so alpha is a constant and c is also a constant, and this is in fact a linear differential inequality which you can solve. So, the solution of this linear differential, so if this term, suppose c is not there, then this is simply v exponentially decaying to 0 from its initial condition v of 0. Now, because of this term c, what we see is that v will not decay down to 0. In fact, it will reach a region and stay within that region for all future time. So, it will exponentially decay to a region, and then for all future time it will stay within that region. So, that this is how this this v of t evolves with time. So, we can say that v of t, so solving this linear differential inequality, what we get is v of t to be less than e to the power minus alpha t v of 0. So, assuming that time starts at t equal to 0 plus c over alpha 1 minus e to the power minus alpha t. So, this is for you as an exercise to solve this and prove that from this we get this. So, it is not very hard to solve it. You have to use your linear system concepts, because this is just a linear system which is driven by an input which is constant in this case. Okay. So, what this means is so from this expression we can say that we can combine these exponential terms together, and we see that starting from v of 0, v of t exponentially decays until it reaches a region c over alpha, and within that region it stays for all future time. It is not able to come out of that region. So, what I am trying to say is that if we construct how v of t evolves with time. So, starting, so let us say we have this region given by c over alpha, and let us say that v of 0 initially starts from something which is greater than c over alpha. So, so starting from this, it exponentially decays until it reaches this region, and then it goes inside this region and stays there for all future time. Okay. So, it's similar to what the kind of argument that we had made earlier, that that as if the states are outside the set, then v dot is less than 0, which means that v monotonically decreases until it reaches this compact set and it stays there for all future time. So, since v does that, and v is a sum of squares of these error states. So, we say that these error states e of t, k x tilde and k r tilde also behave in a similar way. You can prove that mathematically. So, this kind of a result is called as uniform ultimate boundedness. In short, we say it is UUB. So, it is not a Lyapunov stability result. We do not use any of the Lyapunov theorems here, but what we have been able to show is that all the error states, they remain bounded. In fact, we say more than that. We say that these error states starting from a region which is greater than the c over alpha, they exponentially converge, and in finite time they enter this compact set, and for all future time they stay within this compact set. So, somehow if we can reduce the size of this compact set, we can in fact say that these states become very close to 0, which is what is desired. Okay. So, if you want to know more about this UUB result, you can refer the book by Khalil, and you can look at the section 4.8. Okay. So, what sigma mod does is that it does not require the upper bound on the disturbance, and it is still able to guarantee Lyapunov some kind of boundedness result. In fact, we have a uniform ultimate boundedness result, which is fairly good for practical systems which are subjected to external disturbances. But even in this case, if suppose we use this modification, and the real plant does not have any disturbance. So, it is actually a disturbance free case, but we use this modified sigma modified update law, then because of the damping term, because of this leakage term, we will always have we will always have this region within which the states finally lie. So, we will not be able to prove that the tracking error will asymptotically go to 0 for the disturbance free case. All we can say is that the tracking error will be uniformly ultimately bounded. We may be able to reduce the size of this UUB region, but we cannot say that the tracking error asymptotically goes to 0 for the disturbance free case. But for the case where there is a there might be a disturbance, this sigma modification is robust to such disturbances. Okay. So, they provide this damping term, which slows down the convergence of k x hat and k r hat, and thus provide the stability in this case. Okay, so so if we look at the adaptive law for k x hat and or k r hat, we find that there is a small issue with these laws, and there is scope for further improvement. Okay, so as I said, this is the real adaptation term, right. This term provides the adaptation for k x hat, and this term, which is the damping term, is added for stability, and it prevents the phenomena of parameter drift. So, in the case that there is a disturbance, this makes sure that the estimates are always bounded, and we do not need to make any assumptions about the knowledge of the upper bound of the disturbance or the knowledge of the unknown parameters. So, in this way sigma mod is a fairly effective method, but what happens when the error becomes very small? So, as the error becomes very small, we see that the effect of this adaptation term becomes very small, and this term, the sigma mod term, may become dominant in this in the case where E becomes very small. So, what happens in that scenario is that k x hat dot is mainly driven by the second term, and what does the second term do? It tries to drive k x hat to 0, okay, which may not be the true, in fact, which is not the true value for k x hat. K x hat has an ideal value of k x. So, this adaptation term is trying to make sure that k x hat in some ways become close to k x, whereas this stabilizing term is trying to drive k x hat to 0. So, although it guarantees that we have boundedness, but this also leads to unlearning. So, this term leads to unlearning whatever k x hat has learned so far, because E becomes very small. This adaptation term has less effect, and k x hat slowly starts to decay to 0. So, this is the unlearning phenomena of k x hat and k r hat. So, that degrades performance. So, as I said, if you bring in robustness, your performance will degrade. There is always a trade off between robustness and performance, and this clearly shows that the performance might degrade, although we have been able to show that this is robust to external disturbances. Okay. So, so as much as possible we would like this adaptation term to dominate, because that is a real learning term, and this damping term should only be able to keep the parameters from drifting away in the presence of disturbances. So, this is what we want. So, if the sigma x, which is the gain of the sigma mod term, is very high, then that could lead to the unlearning phenomena, or in the case where the tracking error becomes very small. So, we have to guard against such phenomena. So, how do we overcome such a case? That we will cover in the next lecture, but I would like to give you just a little bit of a hint as to what we might be able to do. So, suppose we modify the update law as minus gamma x B transpose P E x transpose minus gamma x sigma x norm of E times k x hat. Suppose I introduce this norm of E in the damping term. So, what does it do? So, one thing is for sure is that when the error becomes small, this term, the damping term, also becomes small. So, the unlearning effect can be mitigated in some way by including the norm of E term in the second term as well of the update law. So, not only will this term become small, but this second term also will become small if the tracking error becomes very small. So, the only thing we need to prove is that with this update law, can we make sure that the signals are bounded, can we make sure that the parameter estimates remain bounded. So, that is what we will prove in the next class. Okay. Thank you.